What if I told you that up to 10% of all the electricity we generate is lost before it even reaches your home? It simply vanishes into thin air, wasted as heat. This invisible tax costs us billions and pushes our power grids to the brink. But a breakthrough in a strange, almost magical class of materials could erase that waste entirely, and in the process, change everything about our technological world. Everywhere electricity flows, it faces a fundamental obstacle: resistance. Think of it like friction. As electrons, the carriers of electric charge, move through a copper wire, they bump into the atoms of the material. Each collision slows them down, and that lost energy is released as heat. This is why your phone gets warm when you charge it, why your laptop needs a fan, and why massive server farms require colossal cooling systems. This isn't just an inconvenience, it's a hard limit on our progress. For decades, Moore's law predicted an exponential growth in computing power. But lately, it's been faltering. We can physically cram more transistors onto a chip, but we can't get the heat out fast enough. We are literally melting the boundaries of innovation. From the massive power lines stretching across our continents to the microscopic circuits inside our devices, this constant, invisible battle against resistance is a tax on every single watt we produce and consume. But what if there was a way to cheat? A way for electricity to flow with perfect efficiency, with zero resistance and zero waste. In 1911, physicist Heike Kamerlingh-Onnes stumbled upon just that. While studying the properties of mercury at extremely low temperatures, just a few degrees above absolute zero, he saw something impossible. Its electrical resistance vanished completely. He had discovered superconductivity. This isn't just better conductivity, it's a fundamentally different state of matter, governed by the strange laws of quantum mechanics. At these frigid temperatures, electrons stop acting as individuals and pair up into what are called Cooper pairs. These pairs can then move through the atomic lattice of the material in perfect lockstep, behaving like a single superfluid that flows without any friction. The applications were immediately obvious. Incredibly powerful magnets for things like MRI machines and particle accelerators, and potentially a revolution in energy. The catch? The insane cold. Until now, achieving superconductivity required expensive and cumbersome cooling with liquid helium, or, for so-called high-temperature superconductivity, liquid nitrogen. It was a Nobel Prize-winning party trick, but far too impractical for widespread use. The holy grail of material science has always been a room temperature, ambient pressure superconductor, a material that could do the impossible right here on your desktop. In 2023, the internet exploded with claims that a team in South Korea had found it, a material called LK99. For a few frantic weeks, labs around the world raced to replicate the findings. The hype was immense, but as the rigorous process of scientific verification unfolded, the initial claims couldn't be independently confirmed. But here's the real story. It didn't matter. The LK99 saga, while a scientific dead end itself, reignited a global firestorm of research. It pulled the field out of its niche and inspired a new generation of physicists and material scientists. The real breakthrough isn't a single magic material. It's the renewed, supercharged race to find one. Scientists are now using artificial intelligence and massive supercomputer simulations to design and test millions of potential atomic structures, vastly accelerating the pace of discovery. While we aren't there yet, the progress since that moment has been staggering. New families of materials, like lanthanum hydrides, are showing superconductivity at ever higher temperatures, albeit still under immense pressures. The finish line of the race may be unknown, but for the first time, it feels like it's finally in sight. So let's imagine we win this race. What does a world built on accessible superconductors actually look like? It starts with the grid. Lossless power lines mean we could build a truly global energy network. Solar power generated in the Sahara could light up New York. Wind farms in the North Sea could power factories in Asia. The intermittent nature of renewables would cease to be a problem. Then our electronics. With no heat to dissipate, computer chips could be layered in 3 dimensions, becoming thousands of times more powerful while using a fraction of the energy. Your smartphone battery could last for weeks, not hours. This would also be the key to unlocking large-scale quantum computers, which rely on delicate superconducting circuits. Transportation would be transformed. Magnetic levitation, or maglev, would become cheap and efficient enough for city-to-city hyperloop networks, traveling at near supersonic speeds. And perhaps most importantly, it could solve our energy crisis forever. One of the biggest hurdles for nuclear fusion, the same process that powers the sun, is creating immensely powerful magnetic fields to contain the superheated plasma. Compact, powerful superconducting magnets would make commercial fusion reactors not just possible, but practical. This isn't just an incremental improvement. It's a foundational shift in our relationship with energy and information, a world without waste. From the simple problem of waste heat to the quantum promise of Cooper pairs, the quest for a room-temperature superconductor is one of the most exciting stories in science today. The recent hype may have faded, but the quiet, determined work it inspired is paving the way for a future that is faster, smarter, and profoundly more efficient. The zero-resistance revolution isn't a matter of if, but when. If you want to stay ahead of the curve on the technology shaping our world, subscribe to Decoded Future and hit the bell so you don't miss an episode. Next time, we're diving into the world of neural interfaces. Can we really merge our brains with AI? And more importantly, should we?